Hello, welcome to today's class. In today's class, we will talk about the performance evaluation of depth first search. So we'll talk about whether DFS is optimal or not, whether it is complete or not, and then we'll talk about the time and space complexity of DFS. To start with, DFS is not optimal, and to illustrate this point, let us take this example where in this tree we have two goal nodes J and C, and in our search, during our search, if DFS proceeds along B, then it would return J as the solution instead of C. And as we can see, J is a suboptimal solution as the cost for this solution is 3, whereas the cost for the solution C is only 1. So DFS, if it proceeds along B, then it would return J as the solution, and hence we see that DFS is not optimal. It will not return the optimal solution always. Next, tree search based DFS is not complete. Again, let us look at the same example, and we know that tree search allows repeated nodes. This algorithm do not check whether the newly generated node is a repeated node or not. So now, if that is the case, it may happen that from A we generate B, and then from B we again generate A, because we are not checking for repeated nodes, and then from A we again generate B, and then from B we generate A, and like this we may go on an infinite path, and hence we may never reach a goal state, and hence it's not guaranteed that DFS will reach a goal state. Even if one is present, we can say that tree search based DFS is not complete. However, graph search based DFS is complete, because graph search based DFS will not allow repeated nodes to happen. It checks for repeated nodes by maintaining a list called explored set, as we have seen in one of the earlier class. Now let us talk about the time and space complexity, and for that we will introduce few terms. The first term is B, which represents the branching factor, and we have seen in one of the earlier class what we mean by branching factor. Then we introduce the term D, which means the depth of the shallowest solution, and we introduce the term M, which represents the maximum depth of any node. So if we take this tree as an example, here we have two goal nodes, and the shallowest goal node is at a depth of 3, and hence D will be equal to 3. And the nodes, the leaf nodes, are the nodes that are at that has the maximum depth, and we say that their depth is equal to M. So M represents the depth of the maximum depth. So with these notations clear, now let us consider this tree for space and time complexity, and we are considering this node to be our goal node. We are considering this node as a goal node because that would produce the worst case scenario for time complexity analysis. And now if we perform DFS on this tree, we will start at the start node, and for the start node we will generate its successors. And now let's say we select this yellow node for expansion next, and when we expand this yellow node we will generate its successor nodes. And again, let's say we select the yellow node for expansion, and after expanding this node we generate the successor nodes of the selected node. And now let us select this yellow node for expansion next, and in this way we will continue and finally generate the nodes, the leaf nodes. And since these leaf nodes don't have any more successors, now let us check how many nodes are there in the explored set and how many nodes are there in the fringe list. We know that these red colored nodes, they are the nodes that will be present in the explored set, because we have performed the expansion of these nodes. Whereas the blue colored nodes, these nodes we have generated but we have not explored them yet, so these blue colored nodes are the nodes that will be in the fringe list. Now this explored set is only maintained by graph search algorithm, because graph search do not allow repeated nodes. It has to keep track of all the nodes that has been generated so far. However, tree search algorithm don't have to maintain this explored set, since tree search allows repeated nodes. However, tree search has to maintain this fringe list. The fringe list will be maintained both by the graph search and the tree search algorithm, because it tells us what are the next possible nodes for expansion. Now if we try to count how many nodes are there in the fringe list, that means if we want to count the total number of blue colored nodes, then we would see that at depth 1 there are b-1 blue colored nodes, because the branching factor is b. So this root node has b successors, and out of that one has been explored. So the remaining b-1 nodes from depth 1 would be present in the fringe list. From depth 2, again we will have b-1 nodes that would be present in the fringe list. Similarly, from depth 3, this red color node has b successors because the branching factor is b, and out of that one node has been explored. So the remaining b-1 nodes would be in the fringe list. Same for depth m-1. For depth m-1 also there will be b-1 nodes in the fringe list. And finally for depth m there will be b nodes in the fringe list. So this is the worst case scenario for the number of nodes in the fringe list. And if we try to count how many nodes are there in the fringe list, since we have m-1 layers here and each layer has b-1 nodes, so the total number of nodes would be m-1 into b-1. There are total m-1 layers and each layer has b-1 nodes, so the total nodes is m-1 into b-1, and plus we have to add the b nodes from depth m. So the total nodes in the fringe list would be m-1 into b-1 plus b, and which approximately is equal to B into M. So these many nodes would be there in the fringe list in the worst case scenario. Thus, a tree search based DFS is, if tree search based DFS is used, the total number of nodes that need to be kept in the memory is approximately equal to B into M, and thus space complexity of tree search based DFS is big O of B into M. Okay, thus space complexity of tree search based DFS is big O of B into M. And in one of the previous class we have seen that the space complexity of BFS is big O of B to the power D, where D is the depth at which the shallowest goal node is present. Now, if we assume that the nodes at the same depth as the goal node have no successors, that means if we consider D as the depth of the shallowest goal nodes, then all the nodes at depth D don't have any more successors. None of the nodes at that depth D have successors, which means the maximum depth in that tree will be D. And thus we can say that since M represents the maximum depth, M will be equal to D. Now with this assumption, if we assume D to be 16, and if we assume the branching factor to be 10, so D is 16 means that's the depth at which the shallowest goal node is present. The shallowest goal node is present at a depth of 16 and the branching factor is 10. And we assume that each node requires 1000 bytes. Now, since we have seen that in the worst case, approximately B into M number of nodes would be there in the fringe list. Thus, for the tree search algorithm based DFS, we have B into M nodes. That means 10 into 16 number of nodes we have, and since each node requires 1000 bytes, the total amount of memory required will be 10 into 16 into 1000, and which will be approximately 156 kilobytes. And in the last class, in one of the previous class, we have seen that for BFS, if the depth of the shallowest goal node is 16, then since the time complexity of BFS is B to the power D, we would require 10 exabytes of memory. However, for DFS we need only 156 kilobyte. This is 7 trillion times less space than required by BFS. So as we compare the tree search based DFS with BFS, we see that in terms of space complexity, tree search based DFS is many times better than BFS. And this has led to the adoption of depth first tree search as the basic workhorse of many areas in AI. Because of this advantage of tree search based DFS, it is more favored. Now continue our discussion. So this was our situation. We have generated the successor nodes for this red colored node. Next, we will select one of the successor of this node for expansion, and since this is a leaf node, it doesn't have any more successors, we will not be able to generate any more nodes for it. So expansion of this node is complete, and we will select the next one of the next successor node of this red color node, and it would proceed like this. And so once we finish expansion of all the successor nodes of this node, we would it and we will continue with the expansion of the other nodes under this subtree. And once we have finished exploring all the nodes under this subtree, this would be the next node selected for expansion, and then we would search one by one all the nodes in this subtree, and once this subtree is complete, we would move to the next successor of this red color node, and with this node explored, that would complete the expansion of sub-3 under this node, and then we would proceed in this way, and at some moment of time the situation may look something like this. And if we again if we again count the number of nodes in the fringe list, that means if we try to color the blue colored nodes, we will see that it would be less than b into m. So in the worst case, the space complexity would be b into m. And now we keep on proceeding in this way, and eventually we will be at a situation where we have explored all these nodes, and finally we are trying to explore this goal node. So as we try to explore this goal node, we see that we have visited all these red colored nodes. Only after visiting all these red colored nodes, we go and reach our goal state. So this is the worst case scenario, where we reach the goal state only after exploring all the other nodes in the tree. And now if we try to count how many red colored nodes we have, we would see that we have seen this expression in one of the earlier class. So it would be 1 plus b, and number of nodes in depth 2 is b square. The number of red color nodes in depth 3 is b cube, and so on. And if we add all these numbers, it gives us big O of bm. Thus the time complexity of DFS is big O of b to the power m. And I would like also to mention one point here, is that in case of graph search, we maintain the explored set, and in the explored set we keep all these visited nodes. All the explored nodes would be kept in the explored set. So in case of graph search DFS, in the memory we would need to keep all these b to the power m nodes, and hence the space complexity of graph search based DFS would be big O of b to the power m. It's only that space complexity of tree search based DFS is big O of b into m, as we have seen few slides before. Now this space complexity that we have discussed, it can be further reduced with backtracking search. So what is backtracking search? Let us try to understand with this tree, which we have seen in the previous class again. But now if we apply backtracking, we'll start with the start node, and Now when we generate the nodes for a given node, we will not generate all the successor nodes. We are not generating C. A had two successor nodes, B and C. We are generating only one of the successor node, B. The other successor node we have not generated. So A has only been partially explored. It has not been fully explored. Next we select B, and again we don't generate all the nodes of B. We generate only one node. And as you can see, these nodes A and B, they are not colored red because we have not completed the exploration of these nodes. They are only been partially explored. So we color them yellow to represent that. Next, then D will be explored, and when we explode D, we generate again only one of the successor node. And next, H will be selected for expansion. And since H do not have any successor node, that would complete the expansion of node H. And next we will select, next we'll generate the next successor node of D, which is I. So what happens here is once we complete the exploration of this child node, we would go back to D and generate the next node of D. So this is what is called backtracking. And if you notice, the maximum number of yellow nodes that are present is 4. Which depends on the maximum depth M. Now again, I is a leaf node, so we cannot generate any more nodes for I. Hence, the exploration of I is complete. And then we go back to D and try to see if it has any more successor nodes. And since D don't have any more successor nodes, the exploration of D is also complete. And now when exploration of D is complete, we backtrack to B and we check whether B has any successor nodes. And we see yes, B has a successor node E. So we generate E, and next we select A for expansion. And when we expand the E, we don't generate all the successor nodes. We generate only one successor node, which is J in this example. And now for J, we cannot generate any more nodes because this is the leaf node. So the exploration of J is complete. We backtrack to E, and then we see if we can generate any more successor nodes for E. Yes, we can generate, and that node is K. For K, we cannot generate any more nodes, so exploration of K is complete. So now we backtrack to E and check if E has any more unexplored successor. E do not have any more unexplored successor, so exploration of E is also complete. And we backtrack to B and check whether B has any unexplored successors. B don't have any unexplored successors, which means exploration of B is also complete. And now we backtrack to A and check whether A has any unexplored node. And yes, A has an unexplored node, C, and in this way we will proceed the search. So one difference we see that with backtracking, we don't generate all the successor nodes. We generate only one successor node at a time. So you apply that backtracking to this tree. What may happen is that we generate only one node for this root node, and for this yellow node we generate only one successor node, and for this node at depth 2 we generate only one successor node, and in this way. So the maximum number of yellow nodes in the worst case will be equal to M plus 1, which is big O of M. So we would require only big O of M space in the worst case. Another, if we continue performing the search, we may have a situation like this also, where we have already explored these nodes, and now again for this root node we have only one node which is currently in the list, and then for this node, yellow node in depth 1, we have generated we have already explored the other red colored node, and now we are trying to explore this yellow colored node. The other successor nodes has not been generated because we are using backtracking. And again, as we can see in this case also, the maximum number of yellow colored nodes is equal to m plus 1, which is big O of m. And hence, with backtracking, the space complexity of 3 base DFS is big O of m. So this completes our discussion on performance evaluation of DFS. So I'd like to end my class here, and we'll meet in the next class. Thank you. Bye.